Hi, welcome to the ExcelWorks series of video tutorials. In this video, we will demonstrate the use of the worksheet integration function QUADF in the ExceLab Add-in library. Let's begin by accessing the help page for QUADF from the website excel-works.com. With QUADF, you can compute a definite or improper integral of any formula in Excel. You can also nest QUADF to compute higher order integrals of any order. Multiple integrals will be demonstrated in a separate tutorial, however. QUADF takes 4 required parameters that map directly to the integral definition: a reference to the integrand formula, the variable of integration, the lower and upper limits. It also takes 2 optional parameters. The first one is a set of key value pairs for algorithm selection, tolerances, and advanced settings for these algorithms. QUADF implements the algorithms in the QUADF library. These include non-adaptive and adaptive algorithms with local and global error controls, as well as fixed rules algorithms. You can find a description of these algorithms on the help page by clicking on any of these algorithms. As well, you can consult the provided reference. The second optional parameter allows you to specify non-singular points for the integrand, if present. Let's begin by starting Excel, which has the ExceLab Add-in enabled. I have prepared 4 functions to integrate. However, in this tutorial, we will only cover the first 2, which are simple formulas. The third and fourth will be computed in part 2 of this video. Let's start with the first example. To compute the integral of f of x, we simply define it as a formula in Excel as follows. Note that I've chosen x1 as my variable of integration. This is completely arbitrary. x1 really maps to x here, which is a dummy variable. Its content doesn't matter. However, since it's undefined here, Excel evaluates this expression to 1 because exponential of 0 is obviously 1. To integrate this formula, I simply enter the QUADF function, passing in a reference to the formula in B2, my variable of integration x1, and my limits, let's say, from -1 to 1. Evaluating this formula computes the integration. We can also integrate this formula from -infinity to infinity in the same manner. For -infinity, I pass the string -inf, and for positive infinity, I pass the string inf. This should equal the square root of pi, which is the exact answer for this integration. We can verify this, and next, let's demonstrate changing some of the optional control parameters, such as the algorithm and tolerances. As I mentioned earlier, these are specified as key value pairs. There are multiple ways we can specify them. For example, we can pass them in as a constant array of strings. Open parenthesis. The first element is the key, which is a string, and the value for my key I can select from any of the admissible values. So I'm going to pick up the fixed rule QK15, again as a string. Starting a second row for the second key, which is atol for absolute tolerances, and this takes a value of real. Close my array. and evaluate the function. Another way to pass these parameters is by defining them in an array in Excel and passing a reference to this array. And then I can highlight this array and close my function call and compute the same answer. Notice that here I did not have to enclose the keys with quotation marks, but when passing them as inline constant array, I have to enclose strings with quotation marks. Before we conclude this example, I would like to point out two facts. First, for improper integrals, which involves infinite limits, the integration algorithm defaults internally to a special algorithm regardless of your selection, so you could not change the algorithm when you have infinite limits. You could change, however, other parameters such as the tolerances. The second point pertains to Excel. Note that we have defined our formula as exponential minus x1 times x1. You may be tempted to define this formula, for example, in the following form. However, very important to note that these two definitions are actually not the same function. This is because Excel gives precedence to the left unary sign operator, the minus the sign here. It gives it precedence over the right power operator. Excel will actually interpret this definition as follows. Which is not exactly the function we want to integrate. So to correct this problem, there are multiple ways we can handle this. One way is to use parentheses. So I'm going to change my function here by using parentheses. Around the term x1 square. So now obviously this does not change the answer because now it's an equivalent function. Now this actually tells Excel to apply the unary operator, the negative unary operator, to the entire term x1 square, not just x. Another way to do it is in fact by adding 0 before the unary operator, and then we can get rid of the parentheses. By adding 0, effectively we switch the unary operator into a binary minus operator, and obviously the power operator has precedence over the minus operator, so this evaluates to the equivalent function here. This concludes our first example. Let's move to the next example. This is very similar to the first example, except that it has a known singularity at x equals 0. We will show how to deal with it via the optional argument. Let's begin by defining the function in Excel as a formula. Obviously, Excel reports a division by 0 error as expected, since x1 is undefined and it's 0 by default. Let's try to integrate this formula. Again from -1 to 1, and we receive an error. It's time to describe the format of these errors. There are two types of errors that can be generated by ExceLab functions, either warnings or errors. They have a common format. The title of the error gives you the location of the cell in the workbook that generates the error and the function. And additional information about what has caused the error. Of course, in this case, it's obvious. It's complaining about processing of argument number 1 because of a division by 0. So it's good to mention that there's another function that you can use to either turn on or off these error messages. That function is called verbose. If you pass an argument of false, that will turn off warnings and error messages completely for all functions. So now if you run into an error, it will just default to the standard Excel error strings without any further information. If you invoke this with true argument, then it defaults back to the user error dialogues. Now, how do we go about fixing this problem? As I mentioned earlier, we have an optional argument in QUADF that allows us to specify singular points for the integrand. So we're going to make use of it, and it's as simple as skipping over the fifth argument, the first optional argument, because we're not changing any settings, and specifying the number 0 since we have only one number here. And by doing this, we are able to evaluate the integral without a problem. Keep in mind that not every singular function is integrable, however. In this example, the singularity is removable and the integral is defined. However, integral of functions with a real or non-removable singularities is generally undefined, and any value computed by QUADF for such integrals are only approximations. Before we conclude this video, I would like to demonstrate one last point. As I mentioned earlier, the choice of our variable of integration x1 in the definition is arbitrary. It has to be a valid cell address, but its content is ignored. For example, we could have used e1 instead of x1. Let me try this. We also have to change it here. Now we can also rename the cell E1 into X by simply typing X here. Now we have named E1 globally in the workbook by X. If we reference X, it will reference E1. And on this sheet, you can manage the names from the name manager, where you can create new names, or and you can also define the scope for these names, so they only apply to specific sheets or the entire workbook. By defining X, we can now reference E1 as X by defining the function as follows, which makes it a bit more readable. We could also define the formula itself as F by renaming the cell B2 as F in the same manner. Now I can come to my integration, and instead of using B2, the row references, I can use F and X, which makes it also a bit more readable, and it will work in the same way. This concludes the second example. I hope you find this video helpful. Thank you for listening, and please continue to check excel-works.com for updated videos and information.